greatest weakness is unawareness. This phrase was coined already 2,500 years ago by famous Chinese military strategist Sun Tzu, whose philosophy is still used today in areas such as leadership and management. And also, vehicle manufacturers are aware of Sun Tzu's wisdom and apply his knowledge in a targeted manner when it comes to positioning their own brand and products in their markets. Identifying market leaders, become market leader, remain market leader. To recognize competitors' strategies and determine reference values in order to derive improvement potential for your own models and define target values. To understand what really motivates end customers subjectively and translate this understanding into objective, measurable values. These are all goals of a really exciting area of work that does so much more than simply compare a few values, namely benchmarking. Well, benchmarking requires a whole lot of knowledge, or to be more precise, lots and lots of measurement data from real vehicles. And this is exactly what we at CSM are specialists in: analog and digital data acquisition of a wide range of measured variables in road tests and on test benches. In the next 30 minutes, we will first take a brief look at the topic of benchmarking and e-mobility in general. Then we will hear something about the requirements that benchmarking applications place on our measurement systems. And finally, we will plunge into our pool of applications together and take a look at a few typical benchmarking applications and how we at CSM have solved these in practice. Let me introduce myself very briefly. My name is Timo Eich. I am Business Development Manager at CSM and your tour guide on today's little benchmarking exploration tour. Why actually do benchmarking? You may be asking yourself. It all sounds relatively time consuming if so much measurement data has to be collected, and you or your company perhaps live by the slogan, "I do my thing." Of course, you can do that if you are more or less alone in the field, but of course, that's not the case in the automotive industry. International competition is now extremely fierce. In the last 5 to 8 years alone, over 20 new car brands have entered the European e-mobility market, and all of them naturally want to get as big a slice of the pie as possible. And so it makes a lot of sense for all of these participants in these markets to look at how their own models compare to the competition and to compare certain values with each other, both technically and commercially. Then, of course, the developers also want to understand how and with which technologies and strategies the competition solves technical challenges so that they can then decide how these challenges can be addressed in their own models. This also means that the benchmarking processes often goes hand in hand with the fundamental search for new technologies. And this is why benchmarking is also essential in the very early development phases of new models, simply in order to be able to define important properties and target values for new models. And finally, model development also raises many questions that are particularly relevant for end customers, such as vehicle character, sustainability, or comfort. And this is where the famous gut feeling often plays a decisive role, meaning very subjective impressions that then lead to a purchase decision. Perhaps you know that from yourself, yet you simply have a closer relationship with a certain vehicle brand than with others, and cannot really pin this down to a specific objective criterion. Benchmarking is therefore also about translating these subjective impressions of end customers into measurable, comparable, and above all, objective parameters. Only then it is possible to make direct comparisons between different vehicle models. And overall, benchmarking is therefore about a future-oriented analysis of the interests of market and the models of competitors, as this allows the company's own model strategies to be aligned as profitably as possible. How exactly is benchmarking implemented? Well, first of all, the properties to be examined are defined, and these can be a whole range of properties depending on whether we are aiming for overall vehicle benchmarking or even go down to component and small part level in design benchmarking. We have listed some typical characteristics here, ranging from performance, drivability, handling, driving comfort, energy consumption, vehicle acoustic, thermal behavior, charging performance, and so on. And as you can see, quite a lot comes together because behind each of these properties, there are many metrics that need to be measured and compared. And behind these metrics are many physical measured variables, which then have to be measured in practice using sensors and measurement technology in the vehicle. Here you can see an example of metrics for determining the performance of an e-axle. The metric to be determined is listed on the left-hand side here. For example, the maximum electrical power of the e-axle here in the first line. So to determine the power, however, we need two real measured variables, namely high voltage and current, and then some complex math to calculate the active power. So for each of the metrics listed on the left, we must therefore consider how precisely, meaning with which sensors and maybe some calculations, we can determine the corresponding metric. Well, once we have determined the physical measured variables and the sensor required for this, we of course also need suitable measurement technology to which our sensors can be connected and read out. And now it gets exciting because the measurements are typically carried out with a serious production vehicle. And this production vehicle then has to be extensively instrumented. Well, we will get to what's so difficult about this in a minute. The measurements for benchmarking should be as realistic as possible and also as objective as possible. This means that the testing of different vehicle models should take place in standardized processes as far as possible. And for this purpose, defined environments are used. For example, the road test is then driven in the standardized WLTP cycle, or the vehicle is placed on a roller dyno and driven through completely automatically. Well, we do everything we can to ensure the best possible comparability of these standardized measurement procedures across different vehicle models. And once the measurement data has been recorded, it is usually stored in huge databases where comprehensive calculations, analysis, and above all, comparisons can be carried out. Now let's take a look at the challenges that benchmarking applications confront our measurement technology with. I earlier mentioned that the instrumentation of production vehicles can be quite exciting. And this is because, unlike in development vehicles, we are dealing here with a fully coated vehicle, which now needs to be comprehensively instrumented. So the installation space for our measurement technology therefore becomes a real challenge. And the measurement data has to be recorded everywhere in the vehicle, in the engine compartment, in the trunk, in the interior, on the chassis and the running gear, on rotating parts, and very important in e-mobility, in the high voltage environment. This means that the measurement technology used must be compact and robust and as possible, and that high voltage safety must also be guaranteed according to where we measure. Such extremely complex instrumentation usually takes longer for a production vehicle than for a development vehicle and can quickly take several weeks. However, this also means that the measurement technology must be very easy to install. In other words, it must offer suitable mounting aids for serious production vehicles. Our CSM mini modules, for example, have housing eyelets for cable ties as a standard, which many of our customers find very practical. And the configuration of the measurement technology, the connection and the commissioning of the sensors, calibration, adjustment, and so on, all of that must also be user-friendly and fast so that the measurement technology simply does not become a burden, but simplifies the instrumentation as much as possible. Then, with the many different parameters that all need to be recorded at the same time, it is important to have flexible measurement technology that allows the recording of numerous different measured variables, and that the same measurement technology is always used for the different vehicle models, as well as for measurement on test bench and in road tests. Because with the sometimes very small differences between the vehicle models, we need absolutely comparable measurement data, and it would be problematic if the differences in the measurement results were already caused by the use of different measurement systems. In other words, we need robust and modular measurement technology for numerous measured variables, which can be easily combined into a flexible measurement system and quickly adapted to changing situations. And we have already talked to some extent about the need for high measurement accuracy. And then this accuracy is simply important in order to reliably capture fast phenomena such as spikes and ripples and even the smallest differences in the measured values, both in terms of amplitude, accuracy, and time resolution. All in all, these are high demands on the measurement technology to be used. So in the following, we take a brief look at the solutions and measurement modules our customers use to handle benchmarking applications. For example, this is what our measurement technology portfolio from CSM looks like, which is used in practice in our customers' benchmarking applications. As you can see, we have plotted the measured variables horizontally, for example, current, voltage, temperature, conditioned measurement signals, strain gauges, IEP accelerometers, and frequencies. And on the vertical line here, you find a classification for the various bus systems offered, and thus also for the scanning frequency range. While with the CAN bus, for example, we typically work with frequencies between 1 Hz and a maximum of 10 kilohertz per channel. With the EtherCAT modules, the transmission rates are between 10 kilohertz and 1 megahertz per channel, and the XCP modules for fast voltage, current, and power measurement reach up to 4 megahertz per channel. In addition, you will also find a vertical division into conventional measurement technology. You could also say low voltage measurement technology, meaning all voltage environments up to 60 volts, and high voltage environment. And the high voltage safe measurement devices can then be used in voltage environments with up to 1000 volts. And a special feature of current measurement is clamp and ring current transformers, as well as measuring resistors, the so-called shunts, which you can see here at the bottom left. Well, this is an overview of the measurement modules for road tests and test benches that are suitable for benchmarking applications. And these modules are part of a complete modular measurement system, namely the Vector CSM e-mobility measurement system. The measurement modules just shown can now be found here in this overview in the large blue box labeled e-mobility basic measurement systems. So we have high voltage breakout modules for current, voltage, power measurement at high voltage potential, super fast XCP models, fast EtherCAT measurement modules and the somewhat slower CAN modules, all of them available for high voltage and low voltage applications. And here you also find an excerpt of the measured variables that we can record with these measurement modules, but there's much more to this overall measuring system, because it includes protocol converters such as XCP gateways, powerful measurement data acquisition software tools such as Vector Canopy or vMeasure, both with the integrated e-mobility analyzer, which performs all the complex power calculations in real time, for example. Also included are data analysis tools such as vSignalizer and vMDM for managing huge volumes of measured data, excuse me, database using databases. And included are also bus interfaces and ECU data acquisition. For example, the VN and the VX interfaces from Vector, as well as the VP series smart loggers from Vector, on which the e-mobility analyzer is also available, and finally, fleet loggers from CSM. It's a truly comprehensive toolbox for all measurements in e-mobility and therefore also for vehicle benchmarking. And to make this quite abstract illustration more concrete for you, let's take a closer look now at a few examples of how these tools are used in practice. Well, just imagine that you are traveling with your electric vehicle in a relatively hot region, perhaps in Australia, and you now have long distances to cover between your destinations. And as it is summer season in Australia, it's very hot outside. Then there could possibly be a conflict of interests. On the one hand, you want the air conditioning to provide sufficient cooling in the passenger compartment. On the other hand, you simply want to arrive at your destination. Because after all, the joy of the beautiful beach here may only be able to console you to a limited extent if the air conditioning functions have gradually drained your battery. The development of electric vehicles is therefore also about finding a balance between comfort and range. And to do this, we have to investigate, among other things, to what extent the numerous auxiliary consumers from the low voltage onboard network consume energy, which in the electric vehicle comes from the traction battery, which primarily has to supply the drive. Incidentally, this is another very typical requirement of end customers. And I don't know about you, but in winter, for example, it's important to me personally that the interior air warms up quickly, the windows are free of ice and condensation, and the seat heating makes it nice and cozy. So we have numerous auxiliary consumers that we have to supply or want to supply, even if they are only comfort functions. And of course, we want to know how much energy these consume in different scenarios, which is then, of course, no longer available to us in the drive. Then we also want to investigate interactions between the low voltage and the high voltage electrical system. For example, what losses occur during voltage conversion, or whether high frequency components propagate to the low voltage electrical system. And of course, we also want to know what the real temperatures are at various points in the interior and on components. And finally, we also want to determine the efficiency of the drivetrain and investigate how the control units behave. And the complete vehicle electrical system could look like this, of course, in a very simplified manner. We have the high voltage traction battery in the middle, which of course supplies the drives, but also the air conditioning functions, meaning heating and cooling and some hydraulics here at high voltage level. And on the right hand side, we then see the conversion of the high voltage to, for example, 12 volts for supplying all the auxiliary consumers that do not require high voltage, for example, assistance systems, windshield wipers, electric window locking system, infotainment, and so on. And if we now want to determine the power consumption of these auxiliary consumers, we need compact and very precise current sensors. And in many cases, quite a lot of them at once. For comprehensive investigation, this can easily result in a 3-digit number of current sensors. And one of these current sensors that our customers like to use in the low voltage range is the CSM shunt. As you might know, a shunt is a precision measuring resistor that is integrated into the cable to measure the current. In addition to the measuring resistor, our CSM shunt also consists of a compact, robust housing suitable for road tests and an active measuring amplifier for signal conditioning. Here we see the slightly larger version of the CSM shunt for the 125 and 250 amps measuring range. And here we also see the smaller, even more compact version for the 2.5 and 25 amps measuring ranges. And the special feature here is the version with the plug for the fuse box. This means that we simply unplug the corresponding fuse, plug in the CSM shunt, plug into the fuse box instead, and then plug the original fuse into this fuse holder here, which is integrated into the CSM shunt's cable. And in this way, the fuse function is retained, and we can measure the current consumption directly at the fuse box very easily and, above all, non-destructively. And the CSM shunt is then simply connected to an analog measurement module, for example, a CAN 80mm measurement module, and we will take a quick look at these modules in a minute. But before that, I'll show you another sensor variant for current measurement, namely the CSM current clamp, a clamp type current transformer that now also allows simple, fast, and very important in benchmarking, non-destructive installation and accurate current measurement. The difference to the shunt is that the clamp does not have to be integrated into the circuit, but is simply clamped around the connector. And as this is a non-contact measurement method from an electrical point of view, we can even use the CSM current clamp in high voltage applications without any concerns. And the great thing is that we even have a usable bandwidth of up to 2 megahertz available for the e-mobility sector. Of course, we can no longer achieve 2 megahertz with a CAN measurement module, so we at CSM use EtherCAT measurement modules for this. And this is where we now also see our 80 measurement modules for CAN or EtherCAT. And these devices offer the corresponding measuring ranges for conditioned measuring signals and extremely low noise signal processing with high effective resolution and measuring accuracy. What's more, these modules also provide sensor supply for the sensors to be connected, and the CSM shunts, for example, can then be supplied with voltage directly from an 80 measurement module. Let's move on to another application, namely the investigation of the efficiency of voltage conversion by DC-DC converters from high voltage to low voltage. And for this, we need not only the power consumption, but also the power before and after the voltage converter. And here in the picture, we can see a very common related application, namely determining the efficiency of the traction inverters. And it's precisely for such simultaneous measurements of voltage and current that our high voltage breakout modules are made for. The great advantage of these modules is that we can calculate the power parameters such as active power, reactive power, apparent power, power factor, and the effective values of current and voltage on board directly in the device in real time, and then transmit them directly in digital form. The high voltage breakout modules also measure the current using the shunt technology, and so we have to cut the cable to integrate the shunt into the cable. And since this is often problematic for benchmarking applications, we have come with a special solution. Because at CSM, the high voltage breakout modules can be fitted directly with cable adapters consisting of the original connector systems from the vehicle. And then the original cable is simply unplugged and removed and replaced or extended with the cable instrumented with the high voltage breakout module. In other words, completely non-destructive integration of the measurement technology for benchmarking purposes. Another application we had was checking the air condition and component temperatures, and our temperature measurement modules for thermocouples and RTD resistance thermometers, which we can see in the picture below, are ideal for this. And for temperature measurements at high voltage potential, we also have the corresponding high voltage safe variants in our portfolio, with which we can precisely and safely measure various temperature sensors at up to 1000 volts potential. Now, I would like to show you two beautiful photos from the field. Many thanks to our customers at APL Landau, who have kindly provided us with a small insight into their benchmarking test setup. We can now see the engine compartment in this photo of a car, which is equipped with many of the measurement modules that we have just seen on the previous slides. For example, the high voltage breakout module for current voltage and power measurement here, as well as two of the CSM current clamp sensors for current measurements. The two clamps are here and hide it here. And there are power supply boxes here in the middle. Then we can also see a CAN 80 measurement module for signal acquisition of the two current clamps and a CSM shunt. You see only the yellow cable of it here. In the picture is not the sensor, and another Kistler sensor. And now let's take a look at the other photo, this time of the trunk of the same vehicle. And here we can now see a data concentrator, so-called XCP gateway, for the fast EtherCAT measurement modules, such as the HVBMs and the EtherCAT 80 installed directly underneath, as well as a thermal measurement module and a measurement module for digital signals. And since the aim of this application is to precisely record the smallest power consumptions, we must not load the vehicle battery with the additional built-in measurement technology, which would then falsify the entire data collection. That's why our colleagues at APL Landau have come up with a clever solution, namely the red case here on the right. And this is nothing more than a portable battery for separately supplying the measurement technology. A really, really nice and practical application. Here you can see the overview of the analog measurement modules that we have just used in the example, meaning in principle all measurement modules and sensors for voltages, currents, and temperatures for low voltage and high voltage application. But that's not all, because in most cases, the data from the control units or the entire bus communication is also important for the benchmarkers. And the decisive factor is here that this bus data is recorded absolutely synchronously with the analog measurement data. Our partner, Vector Informatik, offers the VN interfaces for this purpose, which are also part of the Vector CSM e-mobility measurement system, as mentioned. And these VN interfaces give us access to a wide variety of bus systems in the vehicle, and it is particularly practical that we can also record the fast ECU data and the analog measurement data completely synchronously using, for example, the IEEE 1588 synchronization method. Well, now the question is, how do we record the data? And for this, we can now use the VP series smart loggers from the Vector CSM e-mobility measurement systems, for example, or a measuring computer with data acquisition software such as Vector vMeasure or Vector Canopy. But for example, also ETAS Inca could run here. The nice thing about staying in the vector 2 landscape, however, is that the e-mobility analyzer, this one here, for example, is then available to us in a fast function library for comprehensive real-time analysis in the area of power and efficiency measurement. And with its comprehensive function library, the vector e-mobility analyzer offers us a wide range of calculating functions and analysis that we can easily configure via wizards, and which then make the calculated results directly available to us for online and offline for further data processing. And with these fast functions, we also save valuable time when measuring and analyzing. And thanks to the measurement data obtained in this way, the databases can now be fed into benchmarking, and the data from one vehicle model can be compared with other models that have been tested in the same way in order to draw conclusions for our own strategies for balancing comfort and range, for example. The Vector CSM e-mobility measurement system is therefore a comprehensive and powerful toolbox for almost all measurement tasks relating to benchmarking. But that's not all, because in addition to our partner Vector Informatic, we have also other strong partners on hand to expand our options for benchmarking applications. For example, the acoustic specialists at Mueller BBM Vipro Acoustic, whose hardware and software solutions can be used to conveniently carry out the acoustic interior investigations mentioned at the beginning, and our partner Axon Systems, specialists in the field of telemetry and measurements with strain gauges for many chassis and suspension applications. And together with our partners, we can therefore offer practice-orientated and hardware solutions that reliably solve the demanding tasks in the field of benchmarking. And that is why I would like to invite you to join us. Let's work together to turn unawareness into knowledge so that your vehicles can remain at the forefront of international competition now and in the future.